The purpose of this video is to introduce the analytical technique time-of-flight mass spectrometry, what it is, how it works, and what information it can give us. So starting from the very end of the process, the detection process, the detector here detects the time of flight of different ions, time of flight of ions arriving at that detector. Now those ions, in order to be detected, must exist in the first place. So the first part of the whole process is to do ionization in that first part of the mass spectrometer. Those ions are then accelerated here, and they accelerate so that they have the same kinetic energy. And kinetic energy equals half times by the mass times by the velocity squared. So if the kinetic energy is the same for each of those ions, if the mass is different for different ions, then the velocity must be different for different ions. And because velocity is distance over time, if we rearrange that expression to give time equals distance over velocity, and if we keep the distance of this flight tube constant, so that flight tube has the same distance for all of those ions, then different ions with different masses will arrive at the detector at different times. So the time of flight of ions is different for different masses. So different for ions with different masses. And this is how the analytical technique works. It's a method which can be used to detect the mass of different ions within a sample. Let's look a little more closely at ionization then. So there's two different methods of ionization. The first one is commonly used with small molecules and atomic samples, and it requires the sample to be gaseous to start off with. So a gaseous sample of, say, atoms of X here are hit with fast-moving, high-energy electron. And the high-energy electron is sometimes said to be fired from an electron gun. So it's a high-energy electron moving quickly and hits that atom of X. That causes an electron to be knocked out of the atom of X to produce X plus gas and an electron from X itself, but the second electron was the one that was fired at that at high velocity. So we've got X gas plus E minus producing X plus gas plus 2E minus. A different method that can be used for ionizing a sample is something called electrospray ionization. And this is much more suitable for larger molecules. It provides ions or produces ions when the solvent evaporates from the sample. So the sample in solution and then the solvent evaporates. There's lots of different variants to this depending on the solvent choice, for instance. But for the AQA A-level, the focus seems to be on those which produce MH+. So the solvent causes a protonation of the particular sample molecule when this process is complete. So how this works then, the sample first of all is dissolved in a polar but volatile solvent. That means the solvent itself would evaporate quite readily. It's fed into a hypodermic capillary needle held at a high voltage here, and as it comes out of that needle it produces an aerosol or a fine mist of highly charged droplets. When that aerosol enters this high vacuum region of the mass spectrometer, the solvent evaporates and causes positively charged ions to exist here in the gaseous phase. So those positively charged ions now have gained a proton, so it's important to remember that there's the mass of the proton to think about if dealing with analysis of the ions from this type of ionization. Okay, so remember the mass of the proton is important there. Moving away from the ionization then, the second part of the mass spectrometer is this acceleration, and this is where we achieve this constant kinetic energy, K equals half mv squared. So the mass of the different ions will be different and therefore the velocities will be different, but the kinetic energy is the same for each of those ions. This is achieved by an electric field. Of course, those are positively charged ions, so they can be manipulated using electric fields. Once accelerated to constant kinetic energy, those ions are then allowed to drift through the ion drift tube. And remember that this has got a particular distance, so there is a distance here. Now at the start, those ions begin at the entrance to the ion drift tube, but over time they start to separate out. So hopefully you can see here that the smaller, lower mass ions with higher velocity are moving more rapidly than the larger, lower velocity ions. So you can see here that this red ion is about to strike the detector, and what would be measured is the time taken for that ion to arrive at that detector, having travelled down the distance of that flight tube like so. Once the ion has been detected, of course, the others continue to move, and the time for the next ion would be detected, and so on and so forth. So a series of different signals would be detected at different times, depending on the velocity of those ions in question, which itself depends on the mass of the ions in question. The detection here then, up at this end here, this detection works by the positively charged ions hitting the detector plate where they gain electrons, and there's a movement therefore of electrons from the plate to the ions, and that movement of electrons can be detected as a current. So the time taken is measured. So the data then is used to produce a spectrum. So if this is the overview of the whole process, ionization to make the ions, acceleration to achieve that constant kinetic energy, then ion drift, which allows those ions to separate out because they are travelling with different velocities, and finally the detection will detect the time taken for a particular ion to strike the plate. The signal is reprocessed into a spectrum, and generally speaking the spectrum might look something like this. So on this x-axis down here is m over z. That refers to the mass to charge ratio, and that's important because occasionally the charge on the ion might not be +1. It's usually +1, and therefore most of the signal will relate to just the relative mass of the particular substance. So on this particular diagram, we've got the relative mass on the x-axis, which is the same as the mass to charge ratio because the charge was +1. And the relative abundance goes on the y-axis here. So we can use this to provide the data for the isotope calculations that you've been doing recently, where we can calculate the relative atomic mass, AR, of a particular sample by using the information from the mass spectrum. So if we have a look at this data then here, the relative abundance is 9.0, and that mass number of that particular ion, assuming a +1 charge on that, is 90. So that would be 9.0 times by 90 for that one, plus down here we've got 2.0 at 91, so 2.0 times by 91, plus here we've got 3.0 times by 92, and finally on this end here another 3.0 times 94. That's the total mass of all of those ions. Divide that through then by the number of them that we have added together. So 9.0 plus 2.0 plus 3.0 plus 3.0 to get that relative atomic mass. If I just pop that in the calculator, 9 times by 90 plus 2.0 times 91 plus 3.0 times 92 plus 3.0 times 94, and then divide that through by 9 plus 2 is 11, plus 3 is 14, plus 3 is 17.0 altogether. That comes out with a value of 91.2. I'll give that to 1 decimal place, which is fairly standard for calculating relative atomic masses. So one use of mass spectrometry, the time-of-flight mass spectrometry, is to provide this data, which can then be used to calculate the relative atomic mass of a sample, Other uses include being able to analyse and identify components of a mixture and so on. We will look at this in more depth and detail in a future session.